Hi everyone, we'll just start in like 2 minutes. Alright, hi everyone. I think we'll just get started now. Do you guys hear me well at the back? Yeah? Awesome. Alright. So we'll just let people filter in through, and then we might close the door in maybe like 10 minutes or so. So thank you all for coming. As you guys already know, we're doing the finals crash course for ELEC1111, hosted by ELSOC. This crash course will be led by myself. My name's Laith. And we'll be working with 3 of our newest subcommittee members, Jerry, Ben, and Sid. You guys want to wave to the back. And we'll be going through different parts of the course, and then we'll be going through some questions. Before we get started, if you guys could all scan the QR code and put in your attendance. This supports ELSOC and helps us get funding. So if you could do that real quick, that'd be really great. I'll do it myself, actually. Hey guys, if you could scan the QR code, people just came in, that'd be great, just for attendance. Sid, could you close the door? All right, so a bit about how the crash course is going to go. So that's just the opening slide. So in this crash course, we'll be going over pretty much all the content that you've done in like Quad 1 so far. Because you had your midterm and we've also done the midterm crash course, we'll focus mostly on the later parts of the course, which haven't been assessed yet. So that's your inductors, your AC analysis, and your AC power, and your op amps as well. So most of our questions, or most of our time, we spent on those content points. If in order to do well in those topic points, it's usually, or it's pretty important that you're very comfortable with the content early in the course, because everything in the second half of the course is pretty much an extension of the first half, just using complex numbers instead of like real numbers, especially in AC. So if you're finding that topics 1 to 4 are things that you're still struggling with, I would suggest you might want to look at some of our resources. Our course notes and our midterm crash course are available, one on the YouTube and the others on our Drive. If you just follow that URL link, it should take you to all of our academic resources, and that should be able to help you if you need a refresher on the basics. Just to reiterate myself, if you've come in a bit later, please scan the QR code at the first slide right here, if you haven't already. But other than that, I guess we'll just get started. So these are the content points I'll be going through during this crash course. So these 4 have already been assessed in the midterm. So these last 4 points, or really it's 5, I've sort of put these together. These are the last content points that haven't been assessed yet, and we're spending most of our time on this. So without further ado, I think we'll start with the basics. So this is your power and things like that, and I'd like to invite Ben to do this section.
Can everyone hear me? Okay, so we're going to go through the basics. So this is hopefully stuff you are really familiar with. So just some important things. So first of all, we have power. So we have 3 equations for power. You should really only memorize this one. So we can derive these 2 over here from Ohm's law. And just one quick note about power. When you're finding the power absorbed by resistors, you can use any of these equations here. But when you're finding the power generated by a source, you can only use this first one here. Okay. The passive sign convention, so just remember, if current is going through the positive side of a element to a negative side, then we have power is absorbed, and the other way around, if current flows to the negative side first, to the positive, then power is being generated. And just quick note, conductance, remember, is the reciprocal of resistance. And finally, for DC circuits, for diodes, when they're forward biased, so they behave as a voltage source. So forward bias is when the voltage drop across the diode is greater or equal to the forward voltage of the diode. And other way around, if it's reverse biased, which is when the voltage is less than the forward voltage, then you have a open circuit. Yep. So we're going to move on to Kirchhoff laws. So the Kirchhoff current law is basically the sum of currents in a junction is 0. Hopefully everyone understands that. And for Kirchhoff voltage law, so if we look at a loop, the sum of voltage drops / gains across that loop is going to be 0. And just some important terms, a node is a point on the circuit where the voltage is the same, and a mesh is the smallest possible loop in a circuit. Okay, any questions? No? So we're just going to move on to a question. So let's just cover these tips. So these are just some important tips for nodal analysis. So make sure to always assign your polarities. So it doesn't matter if they're the wrong way around, we'll just get a negative answer. And we have to label all our nodes and set a ground node. So if we know the node, we can just set it to the value of the source or whatever. If we don't know the node, we can just set it to be V1, V2, etc. And we should label all current directions. So in junctions, we should label the currents going into the junction and the currents going out. And if there's a voltage source between 2 grounded nodes, we form a supernode. And we have to establish the supernode conditions, which we'll get to later. And similarly for mesh analysis, we kind of we have to indicate our current direction. So this is a very important one on each mesh. So for me, I personally always pull my currents going clockwise, so like this. So it makes it easier. And we have to assign polarities. So I'll explain the second bit later. Basically, we label our currents I1 and label our currents I1 and I2. And basically what we do is we start with I1, then we assign all the polarities for I1 to be positive to negative. And then we go with I2, assign the rest of the polarities to be positive and negative. So I'll explain more of that later. And if there's a current source between two meshes, we have to form a super mesh. Okay, no questions? Okay. Alright, so we're gonna try this question now. So you can take a photo of this or copy it down in your notebooks. So for the circuit, we have to find V1, V2, and V3 using both nodal and mesh analysis. Let's give a bit of time for everyone to write this in. Okay, let's get started. So, first of all, we're going to do nodal analysis. Okay. So for nodal, we have to, first of all, assign our polarities. So, let me just draw some polarities on here. So, we call this positive, negative, and negative. So it doesn't matter how you assign the polarities. Okay? Now, the next step we have to do is we have to label all our nodes. So right now, we have the ground node at the bottom, which is 0 volts. And we have 3 unknown nodes. So we have V1 here, V2 here, and V3 here. And we've already labeled them, so we're given V1 and V2, V3, you have to find them. So what we do now is we have to apply KCL at each junction. So we can start with V1 here. So for V1, we have to follow the direction of the current with these polarities. So current is going from the positive to the negative terminal. So that means over here the current is going up. So we just call this I1. And we have 4 amps going this way. And over here we have current going down into this resistor here. So we can call this I2. And basically we can just use our KCL. The sum of currents in a junction is 0. So in this case, there's no current entering the junction. They're all leaving. So we can just set 0 as the current entering the junction. And we just have I1 plus I2 plus 4. So the 4 amps is going this way. Okay? So that's our equation. And we can use Ohm's law to equate the currents in terms of voltage and resistance. So what we have is I1 is going to be the voltage drop across V1 and V3. So we do V1 minus V3. And the resistance of that drop is going to be 6 ohms. And for I2 over here, I2 is going down. So we can do V1 minus 0 over 2 ohms. And finally we have 4 from the current. And that basically gives us one equation, so I can label this equation 1. So let's move on to V2 over here. So for V2, we do the same method. We have current going in. In this case, current's going to go that way, and it's going to go this way. Yep. So this is just 4 amps over here. We can call this one I3. Oh, sorry. In this case, we actually have a supernode. So for a supernode, we have a voltage source that's connected between 2 points, which is not the ground. So these two, V2 and V3, they're not the ground nodes. So we have to establish a supernode. So what we do, negative here. So this just simplifies the working out later. Okay. So we can start with I1. We're going to apply KVL and we're gonna equate the voltage drops and gains across this mesh. I'm gonna set that equal to 0. So let's start at the top over here. So we have a 4-volt battery, so we can just say -4. And then we have a 2 ohm resistor here. So we want to write the resistor in terms of voltage. So we're going to use Ohm's law, so V equals IR. So which is just 2I1. And then finally we have the 4 ohm resistor here. So 4I1, which is equal to 0. So since this one is going is between two meshes, we actually have I1. So I1 is going up and I2 is going down. So we'll do I1 minus I2. So sorry, if I1 minus I2 is 0. Okay. So this is our first equation here. Okay. Now, since we have this current source here, we have to form a super mesh. So we're going to combine mesh 2 and 3, and we're going to go around this entire loop here and equate and apply KVL on here. Before we do that, let's establish our super mesh condition. So what we do is we set the current of this source equal to the difference between I2 and I3. So I2 is going this way in the direction of the current source, and I3 is going to go this way. So I can just write here I2 and I3. So what we get is 4 is equal to I2 minus I3. So that makes our second equation. And then we can apply KVL at the super mesh. So let's start off with the 4 ohm resistor. So we're going through the negative terminal, so we have the 4 ohms. Yep. And since it's between I1 and I2, we have to do I1 minus I2. And then we go up the 2 ohm resistor, so plus 2I2. And then we have the 6 ohm resistor, so plus 6I3. And then we have the 4 volt source, which is plus 4. And all of that's going to be equal to 0. So this over here is our third equation. Yep. And now that we have 3 equations, we can just solve simultaneously. We find currents I1, I2, and I3. And once we find the currents, we can just apply Ohm's law to find the voltage drops between these resistors over here, and that's gonna get you V3, V2, and V1. Okay, does that make sense? Okay. So don't have to go over much. So your answers are just here. So you solve this, you get to this. Okay. And just a quick tip for mesh analysis. Since I've labeled all my directions going clockwise, and I've assigned polarities starting from I1, then I2 and I3. Whenever I have a element between two meshes, it's always going to be the lower current minus the higher current. So in this case, it would be I1 minus I2. If there was a element between I2 and I3, then it would be I2 minus I3. Okay. All good? Okay. So, I guess moving on. Okay. What is this?
So, can everyone hear me?
Yep.
Good. So, now we will move up to circuit theorems, which is just aka applications of nodal and mesh and in many cases, multiple times to solve a problem. So, oops, wait. Oops, to fix it, sorry. Accident.
Alright, what was it? Yeah.
Thank you. Okay, so circuit theorems for Code 1 is all based on linear property. So what it's saying is that basically if you have two independent sources, we can consider them individually and add their contribution at the end. Due to linear property, we can derive the question types of superposition, source transformation, and of course like our Thevenin and Norton. So yeah, I hope we remember the formula for the maximum power transfer in Thevenin equivalent circuit is VTH squared ohm for RTH. So linear property and superposition, it's unlikely they will just ask like linear property. It's likely they will ask it in the context of superposition. So we've given in a circuit, we're given two or more independent sources. What we're asked to do is to basically shut down each one of them, shut down everything except for one, and analyze each independently. When do I mean by shut down the independent sources? I mean open circuit the current sources and short circuiting the voltage sources, as we shall see in the next example. Okay, yep, so this is one of the past final questions or so. So we're asked to find I0. As you can see, this circuit might not be like the most cleanest circuit, right? Like if we were just to do nodal or mesh analysis, we have how many meshes? One mesh, two mesh, 3, 4. And if we were to do nodal, it's not going to be much better. So the easiest case for this question will be to use superposition. So for superposition, what we always do is to let the required quantity be split up into components. In here, it's I0. So our first step, let I0 equals to I0 dash plus by I0 double dash. Let I0 dash be due to the 5 amp source. And let I0 double dash equals to 10 volt source. Yep, so now we can basically start doing the analysis. But is there anything we can do before we just jump straight into like open circuiting the 5 amp or short circuiting the 10 volt? Yeah, that's right. Yeah. We can see this is one node here. And this is another node. This means that the 3 ohm and the 7 ohm are actually in parallel. So we can simplify them first. It's going to make our life later much easier. The equivalence resistance is given by, oops, that looks like it. 3 ohm in parallel with a 7 ohm, 3 times 7 ohm, that's a 7, 3 times 7 ohm, 3 plus 7. That's going to give us 2.1 ohm. So simplifying the resistors, we should arrive at the following circuit. Yep, everyone see? We can also simplify the 2 ohm and the 2.1 ohm, like this two, because they're in series. So we can just put them as a single 4.1 ohm. And now we can start to actually do the nodal and mesh analysis. So for case 1, we want to find I0 dash, right? So we short circuit the 10 volt source. By doing that, we should arrive at the circuit as I have drawn in case 1. This looks minus 1.87 amps. Yeah. So is there any questions regarding anything I've done in this question? Oh, last one. So remember if I have a resistor like this, the current is here, right? V1, V2, this is I, let's say this be R. The Ohm's law is defined as I equals to the one that's where it is coming from, the first voltage, V1 minus V2 on R. This is just a definition of Ohm's law. Yeah. because I guess it's kind of because our voltage has to drop across a resistor. So yeah. If a current I actually flows here, then I1 actually needs to be greater than I2. So we find a potential difference. This, yeah. Cool. Good. Next one. So source transformation. There shouldn't be too much theory in here because source transformation questions, it's just to basically just keep using this and to simplify the circuit as much as possible. And sometimes this can actually just give us the answer directly, as we shall see next example. But before I get to the next example, we should probably go over this thing first. The Thevenin and Norton's. Yeah, Thevenin and Norton, the theory is pretty clear, right? Every linear circuit can be simplified as a voltage source in series of a resistor or a current source in parallel of the same resistor. Yep, and VTH, to find VTH, we just do nodal and mesh analysis, find the voltage. But if we're trying to find the RTH, that would be more difficult. So if there's no dependent source, right, it's going to be pretty easy. We can just do series or parallel resistor simplification after turning off all independent sources. But like in midterm, they might not be that nice and just decided to add some like dependent sources. In this way, we have to use either one of these three methods. The first method is to attach a 1 volt or 1 dummy source across the terminals AB of interest. And if we attach a voltage source, we find the current source and find the voltage if a current source is attached, and so on. Yeah. And V equals IR to find the RTH. So the second method is to find the Norton's current first by short-circuiting AB and use the fact that RTH equals to VTH on IN. And the third method is pretty useful sometimes, but beware, which is to use a series of source transformations to simplify the circuit. This can be extremely useful because it reduces the need to analyze VTH and RTH individually. By doing that, we can derive them both like together. However, there's one case we should be careful with the use of source transformations for RTH, which is again when we have a dependent source. For example, right, I have a circuit like here. Oh, I should use a different color. Okay, let's say we have a source, we cannot do source transformation. Why? Then we lose information about I, right? If we transform, let's say, the left current source with a resistor in parallel, yes, voltage source with us in linear with a resistor looks very cool, but we don't know I. Source in series of 4 ohm. We can replace it with a current source of 6 ohm 4 equals to 1.5 amp in parallel with a 4 ohm resistor. So we arrive at this network here. And then the 4 ohm and the 1 ohm will be parallel. We can again simplify them now. Oopsies. This should be equals to 4 times 1 ohm 4 plus 1, 0.8 ohms. Yep. Putting that would be in series of the 3 ohm if we transform. So this thing is equivalent. Those two networks are equivalent. This is 0.8 ohms. And the voltage source, we will be, by the way, we have calculated this as 1.5 amps. So we will be 1.5 times 4, because we're transforming this, like this whole thing. I mean 0.8. This will be 0.8, sorry. I forgot we already simplified the resistor. So yeah, the voltage will be 1.5 times 0.8, which gives us 1.2 volts. So now we arrive at this thing. These 3 ohm and the 0.8 ohm can be simplified, right? So this should turn out sources can be simply be added. So this will be, by the way, should we, so are we going to add the 1 and 4.31 or are we going to subtract it? Yeah. Yeah, that's right. Yep, and finally, we can do our final transformation. which is to do V equals to IR, so 3.31 times by 2.33. So this should give us and RTH will be equals to our resistor calculated previously. Yep, and this is the Sullivan equivalent circuit because we have simplified everything till it's in this form. So now we have found both RTH and VTH without doing source transformation yet.
What happens to the 2 ohm resistor?
Oh, oops, oh, sorry, I forgot. Yeah, we need to add this. We need to add the 2 ohm resistor here back. Yeah. Yeah. So that will be RTH. Yeah. Next questions.
For the current, when you calculated it, how did you get 1.80 over 3.8 equals 4.31?
It should be 1.59 in reality. And this is going to be downwards. That should be correct. A question, but it should cover the gist of all capacitor questions. So we're asked to find V. Wait. So for part A, we're trying to find VT immediately after the change switches to B. So by the way, from the definition of capacitor, can we all agree that V0 plus equals to V0 minus? Yeah, because the voltage and capacitor cannot change, it doesn't take too long. It's pretty simple. That's it. So for the next question, it asks us to find the expression for the capacitor voltage for all time. So this means that we need the voltage as the time approaches infinity. Let's look at the circuit here. To find for time up towards infinity, it's probably likely time is positive, right? So it's going to be after the change. We look here. After applying the change, the 10 amp will be open circuited. So it's gone now. All we need to consider is this part of the circuit. Again, we want to find V voltage here. So which will be same here. Can we see like a voltage division here? Because no current will flow through here. This will be 0 amp. All the currents will flow in here. We can simply use the voltage division, right? So we have 6 and 3. So V infinity equals to 60 times by 3 on 3 plus 6 equals to 20 volts. That will be V infinity. We have a V0. The only thing we need now is the RTH to find the time constant, of course. So now we can again look at this circuit here. We have the 2 terminals here and here. So for find RTH, we just in here. So VT equals to V0, V infinity plus by V0 minus V infinity e to the power minus T on tau. V infinity I have calculated to be 20 volts. Plus by V0, 30 minus 10, e to the power of minus T on 4. 20 plus by 20 e to the power of minus 0.25 T volts, where T is in seconds, and V is in volts. Yep, so, okay, yeah. 30. Sorry, that should be a 2. It looks like a 1. Yeah, that is 1. Yeah. Yeah. Good. Okay.
So for the 7 resistance you used to calculate the time constant, that's going to be the 7 resistance after you change, after the at B, right?
Yeah. because like part is getting bypassed. So we can grab my notes real quick. Can redraw the circuit very simply. Okay, it's not an interesting, but we'll work along with it. So, if we remember that this part in the center, the inductor would actually work as a short circuit, which makes our lives extremely easy because these two resistors are being bypassed. So, this current here, I0, is actually just equal to the current source, which is 9 milliamps. That's 1/3 of everything we need already. The next part is I as we approach infinity. So this B is getting connected. So this section of the circuit is now redundant, for it is getting bypassed. Once again, we can redraw that. 9 volts. 10,000 ohm resistor, 9,000 short circuit through the 0.2 and 15,000 like this. So once again, they've made our lives very easy with the placement of the inductor as it's been short circuited. So these two resistors are no longer applicable. So this I, as we approach infinity, is simply equal to the voltage over the resistance. Should give us 0.9 milliamps. Okay. All good? The next part concerns our tau. And we've already been given the inductance L, which is 0.2. So all we need to find is the equivalent resistance after the switch has turned to 2.
It's just that's why the I infinity, that's just all of it.
Yes.
Okay.
Okay. Any other questions regarding how we got these three values? Yes.
Just when you divide 9 milliamps, are you dividing by 10K or just 10?
10,000. That should be okay.
Would that be 0.9 micro?
It should be. Micro or milliamps? 0.9. Yeah, 0.9 micro, yeah. Milli? Yeah, milli, sorry, not micro, milli. M-amps. Yes, this is correct. Okay. All good? So, the next step, all we have to do is just write it into our actual equation. Oh, sorry, before that, what actually is tau?
Just arc, that's it.
Yeah. L over R. So 0.2 over 3.6 thousand. That should give you 55.5 microseconds. Okay. Now we can put everything into our equation. So, I might just write it out again. T is equal to infinity plus negative t on tau. In this case, plug everything in. 0.9 plus 9 minus 0.9 e to the power of negative t on 55.5 times 10 to the negative 6. We can then simplify this slightly into 8.1 e negative 18,000 t. Does everything here make sense, how I just put everything into the equation? Okay? The next question asks us to find the voltage VT here. This voltage. And there's a little trick here that they did. Can someone tell me what might the trick be that I'm referring to? So positive and negatives. So from the way we drew our circuit up here, we can see that the voltage is going to be higher up here than down here. And in fact, if we observe here, the voltage across this 9,000 resistor is going to be the same voltage that is over the inductor, because they are parallel. So the only trick we need to worry about here is, for one, we need to find the actual voltage over the inductor, and then V of t is simply going to be the negative of this V inductance here. Okay? And our trusty formula here shows that voltage is just inductance multiplied by the derivative of current to time. We already know our equation of current to time, so it's simply going to be this. Its derivative multiplied by the inductance, and then negative in this case, because we're talking about this V. Okay? So that is going to be 0.2 multiplied by derivative of 0.9 plus 8.1 e to the negative 18,000. Minus there, don't forget that. T. Okay? So hopefully we all know how to do this derivative. So the 0.9 gets cancelled, and then the power gets put forward, 18,000, and just multiplied by 8.1 e power of negative 18,000 t. Yes. Also, something very important that I forgot to mention here is we need to be very careful with our units as well. So because we got our answers in milliamps, this is confusing me now, milliamps, we need to remember that this equation will also be in milliamps, and therefore here it will be in millivolts. So after we've done everything, that will give us 29.16 e to the power of negative 18,000 t volts. All good here? Fantastic. Next we'll be moving on to op-amps. So you would have learned that an op-amp has many, many qualities. However, right now, we'll only ever be concerned about two. The first one is that it's got infinite input impedance. So it's going to be zero input current going into the op-amp. So if I label on here, these two currents, they are going to both equal 0. So this current flowing from ground through R1 is going to be the same into this node we'll call V. Will be the same as V going into V out. Okay? And the second one is that the two input channels will have the exact same voltage. So if V in here is equal to 5 volts, this V down here, V1, would also be equal to 5 volts. So you would have been given a lot of formulas about different op-amps and their equations.
If you can't remember them, do not worry. This is all you need to know to solve any major op-amp question. And here we have a standard, just some simple steps to analyze op-amps. First is label your nodal voltages, so where there's an input and output, put them as the same, and identify the trends in the current, so know where the current is equal to each other. And then all you have to do is do your nodal. Okay? Let's look at an example. Step number 1, let's identify where our nodes are the same. So here we've got V1, it's peculiar, it's probably upside down to what we're normally used to, but it doesn't really matter. This node here we know to be minus 0.5 volts. And this node here, connected to ground, is equal to 0 volts. Okay? And now, okay, first off, let's actually read the question, my apologies. For the circuit below, find IA, which is this current flowing through the 1,000 ohm resistor. We'll call that node V1 and that node V2. So to solve this question, we'll need to know V1 and V2, and then just simply use Ohm's law. So how can we find V1? Well, we know that this current here has to be equal to this. Okay, let's change the color to make it a little bit clearer. This current here will need to be the same. 33,000 is going to be the same as 0 minus V2 over 120,000. Once again, move it around. Very simple algebra. You get V2 is equal to negative 3.64 volts. Any questions here? Okay, very nice. So the next step, all we have to do is finish it. This IA is equal to V2 minus V1 over 1,000. So that's going to be equal to negative 3.64 minus negative 2.85 over 1,000, giving us minus 0.79 milliamps. Happy? Happy as Larry? Next question. This will be our second op-amp example. This question here asks us to calculate I0 in the op-amp, which is this little thing here. So how can we find that? Let's go and do a little bit of analysis of the circuit. So that there is ground, so we will need to know what this voltage is. And to know what this voltage is, that's going to be a little bit difficult, because there really is nothing here that tells us. So we might need to have a look down the circuit. But in the meantime, as we go, let's label our nodes. So this one here is connected to the ground, so that's going to be 0 volts. This op-amp is actually surrounded by the same thing, so this whole node is going to be the same. We'll call that V2. And this here, that is 0.5 volts. Yes?
So the feedback loop there,
Yep.
that's the same node as the ones connected to the 3 and 1K ohms? That's the same node?
It's not necessarily the same node, however, because this,
It will be the same voltage.
yes, it will be the same voltage, because the input and output,
I see.
yeah, sorry, the two input nodes will have the same voltage.
And then the current going into the terminals is 0, so...
Yes, so, yeah, let's label that actually, now that we're here. So, if this here is I1, and this here is I2, this here is I3. We can see that I1 is equal to I2 plus I3. Okay? And we can probably do a similar thing here with I4 and I5. I5 is equal to I3 plus I4. All good? Perfect. Next, we'll move on to the fun stuff, AC.
Alright, hope you guys are still with me. Alright, so in this part of the crash course, we'll be covering AC analysis. This is AC analysis 1 and 2, and then I'll do a bit of AC power a bit later. So just to start off, so a bit of content about AC in general. So now in this part of the course, we're working with sinusoidal signals. So those are signals that can be expressed like so. And what we'll see is that in general, when we're working with our circuits, one issue is that, hold on one second. Yep, that's right. One issue that we'll find is that trying to work with sinusoidal signals in our circuit as is really difficult because they're expressed in the time domain. And so one issue we'll have is that if we're working with something like inductors, so we've got L, di, dt, we start working with differential equations. And that becomes really, really difficult. So what we can do is that instead of working in the time domain, we start working in the frequency domain. So we can express these sinusoidal signals as a complex number, where the amplitude corresponds to, sort of the amplitude of the AC signal in the time domain corresponds to the modulus of the complex number, and then the argument or the phase shift. So the argument corresponds to the phase shift. Now, one key thing to consider that a lot of people find pretty confusing is that if we're working with signals, or if we're working with a circuit that's operating at different frequencies, we can't just add their phases together. So for example, if I had, let's just say, a phasor like this, and I wanted to add it to this phasor, let's call that theta, and this is operating at omega equals 10, and this one's operating at omega equals 20, we won't be able to do that. And that's because this is defined for a different frequency to this. So you can't do sort of like operations with them. You can't add them, you can't multiply them. And you see that specifically in questions of superposition, which we'll get to. That should be the first. Yeah, it's the first question. Whoa, what is that? There we are. All right. Also, we work with impedances. So all of our circuit elements have analog definitions in the frequency domain. So obviously, so our resistors stay the same, but our capacitors and our inductors have new definitions. And the great thing about this is that now we can apply a lot of our DC circuit theorems for resistors to impedances. So we can do we can extend V equals IR to V equals IZ. And so now this applies to these two. There's a lot of arrows. So just sort of reiterating, yep, all of our circuit theorems remain the same. So what you'll find is KVL, KCL stay the same, voltage division, our superposition stays the same, our source transformation stays the same, and our Thevenin also stay the same. So all of these sort of are extended to the frequency domain. The only difference now is that we're working with complex numbers. So it makes a bit of the calculations a bit more difficult, but the logic behind it stays consistent, hopefully. One key thing to note was sort of, I kind of mentioned it a bit earlier, is that if we have a circuit that's operating at different frequencies, then superposition must be used. And so if I could give an example, if I have a voltage source here, and this is operating, let's just say that this is at 10 sine of 10, oh, it's a bit cramped, 10t, like that. And then this is maybe some sort of resistor, and then this is maybe another resistor or something like that, and then there's a current source here. And then this one is operating at 10 sine of 30t. We can see that omega here is 30, and then omega here is 10. And so we can't use something like mesh analysis or nodal, because we can't work with the phases. We can't just do normal operations with the phases. So what we have to do is that we have to consider each source individually. So what we'll do is that we have the voltage source. If we're just considering the voltage source, then we would open circuit the current source, so we get rid of that. And then we'll just work with phases in this frequency. And then for this one, if we're considering just this one, we get rid of that. This would become a short circuit, and then all of our impedances, so this was, bad example, I used the resistance there, but if we had capacitors or inductors, then we work with those impedances instead, based on the other frequency, if that makes sense. Are there any questions so far? No? Awesome. All right, we'll get to the first example. I did a bit of prior annotation because there's a lot of circuit drawing in this one. So let's read the question. So this is from the 24 T1 paper. And this is question 4. So this is your second last question. And I think all of them are about like 20 marks. So it's pretty substantial for this part. And there's only one part to this question. So this whole question is just this. So you have to ensure you can get these marks. So what we can see here is that we have to find V out, and V out is the voltage across this resistor, which just so happens to also be the voltage across this capacitor as well, because they're connected in parallel. And so what we can see here is that if we just have a look at the circuit, what we can see is that we've got a current source, we've got a voltage source, and we have another voltage source. Now these are great, these are DC, but this one's AC. These both operate at essentially omega equals 0. So this is omega equals 0 as well. But this one operates at omega equals 1. You can see that because the coefficient here of t is just 1. Just 1 times t. So what that should tell you immediately is that we can't solve this using mesh or nodal. We have to use superposition. Or you could use mesh and nodal, but within superposition, if that makes sense. So what we can do is that if we consider each source individually, I'll just rename these. So this is V0 dash, this is V0 double dash, this is V0 triple dash. What we can say is that if we want to find, that's a bad annotation. Let's call this I, let's call this double I, and we'll call this triple I. So what we can say is that looking at each of these contributions, I'll call this double I. There we are. What we can say is that we want to find V0. That'll be from V0 dash plus V0 double dash plus V0 triple dash. And this is as a result from that source. This one's from this source, and this one's from this source. Does that sort of make sense? Any questions so far? Great. So I already started doing 2, but I'll do 1 first. I'll do 1 and 3 because they're easier, and then I'll finish off with 2. So let's consider just the contribution of 1. So I've got some space down here, that's good. We'll look at the contribution of just I. Right? So looking at the circuit, what can we see? So if we're looking at just this source, using superposition, we'd have to turn off all the other sources. So that means that I can rub a bit of this off so I get some space. What we can say is that this becomes a short circuit. This also becomes a short circuit. This inductor, because we're working in DC, becomes a short circuit. And this capacitor becomes an open circuit. So we'll just draw it like this. So if we redraw what we've got here, is that we've got a current source at the top, it's 2 amps, and then it's in parallel with that 2 ohm resistor, I'll just draw it like this because it's a bit neater. And that will be also in parallel with this resistor, considering that this is now short-circuited. And then this will connect to this resistor. And then this will be plus minus a V out. We know that this is 5 ohms. We know that this is 10 ohms. And we know that this is 2 ohms. All right. So what can we do? We know that these two, well, actually all three of these are in parallel. But the method that I'll be using current divider. So in order to do that, I'll just simplify these two. So I can simplify this to a simpler circuit. What I can get is that if I just redraw it and I sort of rotate the circuit, what we'll get is that this is 2 amps, and they'll be connected to the equivalent resistance between those two, and then this is going to be the 5 ohm. Oh, actually, no, because I don't want the current, I just want the voltage. Never mind. What I can do is I can just simplify all of these in parallel, and then I can do just Ohm's law essentially. So what we get is that we do say R equivalent, well, that's not cooperating. That is equal to 2 parallel 10 parallel 5. And that is equal to, I'll just punch that into my calculator. Right, that should be 514 ohms. And so what that means is that we know the voltages across all of these are the same because they all share the same nodes. So what we can say is that V out, this is dash, V out dash, is going to be I times R, where I is 2, and R will be 5 on 4. Got 10 on 7. Right, and then that's going to be that plus 10 times minus 6, which is equal to 0.75 or negative 0.75 volts. Does that make sense? Hopefully. All right, and then now we'll do the second contribution. I'll move this around a bit so that we've got a bit more space. So V0 dash is equal to 2.5 volts. I'll get rid of this. Okay. Now for the last contribution, all you can see is that we get rid of this, get rid of these annotations because they're cluttering up the workspace. We want to ignore this. We want to ignore this. And now because we're working in AC now, this has an omega that's equal to 1. In AC, inductors and capacitors aren't just short circuits and open circuits respectively, because they're defined by their impedance. So that's going to be 1 on J omega L, and it's going to be Z is equal to, oh, that's not right. That's just J omega L. And this is 1 on J omega C. And then what you can see is that omega is variable. And so these sort of act like resistances now. Now, before this crash course, I actually redrew the circuit. So what we can say is that by ignoring this and then making that a short circuit and then calculating our impedances, our resistances stay the same for this one and that one. I can redraw the circuit like so. So we've got this now. Hopefully that sort of makes sense. Now the problem that we'll see is that, this is pretty convoluted so far. There's a lot of stuff going on. There's several ways you can go about solving this. You could use mesh, you could use 30 times that by that resistance times 5 on 3. And so that becomes a new voltage source. So this becomes 25 on 3 angle 30 degrees. and then we'll add these resistances together. So I'll just save this into my calculator. And so we'll get this, whoop, that's not what I want to do. This becomes 5 on 3 plus 0.5J, so this is now a complex impedance. And then we'll get the last part of this impedance. Now, we know that this part right here is actually the same as this. So I can just simplify those in parallel. So what I know is that we've got the resistance and we've got the impedance. So we'll call this ZEQ, I guess. And so this will equal to 5 parallel negative 2.5J. And so that's equal to, if I just chuck it into my calculator, minus 2.5J. Ooh, okay. So this becomes, that becomes 2.24 angle minus 63.4 degrees. And I'll just save that as well. Okay. And so what we can see here is that now we've simplified the circuit quite substantially. And so we can do voltage divider. So we can look at this voltage only. And that's what we care about. So we'll do voltage divider. What we can see is that V0 double dash is going to be equal to, that's plus, that's minus, is equal to the voltage that we want, 2.24 angle minus 63.4, on top of that extra impedance that we don't care about, plus the same impedance that we do care about, angle minus 63.4. That's a plus. And then we're multiplying that, let me get rid of this. Multiplying that by sort of the input resistance, or the input voltage source, I mean. All right, and so what we get is that if we plug these in, so let's have a look here, yep. So that's B, and then this is going to be B plus 5 on 3 plus 0.5J times 25 on 3, and then that's got an angle to it. And that should be 6.09 angle minus 4.08 degrees. Does that sort of make sense? Just some general advice for the final. When you're working with AC, just put everything into your calculator. Volts. So this is 240 milli, and then if we just represent it as a phasor, we know that the angle is 0. And then for V2, we know that it's also 0 phase, and the magnitude is 210. So this is going to be 210 milli, 0. Awesome. Once. So that would be your follower. You don't really need to memorize, but you're inverting and you're non-inverting potentially, because it might make things quicker during the final exam, and you don't have to prove that these work. And so I can just use this formula, and then the answer sort of just falls out because we know this, or we want to find this, and we can get it in terms of this and this. And the only caveat is that we have to find Z1 and Z2. Now Z1 and Z2 correspond to, let me make this a bit neater. Z1 corresponds to this. This is Z1. And this is Z2. So what we can do is that we know Z1 is equal to, we know it's 12K, plus in series with this impedance, which is 1 on J omega C. Now we know omega is 120 pi radians. So what we'll get is that we'll get this plus 1 on, I'm just plugging this into my calculator right now, and that's multiplied by the capacitance, which is 1 times 10 to the negative 6. And so in polar form, what we'll get is 12,289.7 angle minus 12.5 degrees. And so that's Z1. Z2 is equal to 10 kilo ohms plus, it's also, it's the same capacitor, just go away. 1 on J omega C. And so it's very similar to what we did before. I can just modify previous, oh, hello, there we are. I can just make that 10k ohms instead of 12k. And so our answer sort of falls out. We get Z2 is equal to 10,345.8 angle minus 14.9 degrees. Okay. And so now we've got this equation. We can just start subbing in. We know ZF is simply just 10k. ZF is 10k. So if I just sub it into the formula, what we'll get is that we'll do 1 minus, so we'll get negative, this would be ZF, which is 10 times 10 to the 3. And then we'll divide that by this, which is Z1. Yep. And so we'll get 0.814 angle 1267.5 degrees. This is all multiplied by V1 minus the next one. Actually, no, I'll just do plus that one because the phasor will take, will control the negative sign. And so what we'll get now is that, instead of doing that, we'll go back to this. Nope, that's not what I wanted. Yeah. And then we've got minus ZF on Z2. And that's equal to 0.967 angle minus 165.14 degrees. And that's multiplied by this. And so that's our expression. Does that sort of make sense? Any questions so far? No? Great. Okay. I might make some more space, actually. Where am I? Good. Oh, just kind of pushed it to the bottom. Alright, so that's the first part of the problem. And now for the second part, we have to find just V out in terms of these two phases. So we just substitute them in, essentially. So we know that V out is equal to this, but we'll substitute the values that we know for V1 and V2. So what we'll get is that I'll just plug this into my calculator because it's quicker that way. 167.5, and I'll multiply that by 240 milli, I'm fairly sure, yes. Plus, and then the next one will be 0.967, and then angle minus 165.14. And then we'll multiply that by 210 times 10 to the negative 3. Okay. So V out is going to equal, oh, did I, hold on 1 second. That's why. Okay, so V out should be equal to 0.398 3 or whatever, and then that's angle 166.30 degrees. And so in the time domain, the question asks us to show it in the time domain, so not as a phasor. And so we can just do VO of t, and that's equal to that magnitude, which corresponds 1 to 1. It doesn't actually tell us what function they use to make these phases. They just said it's sinusoidal, so it could be sine or cosine, but we'll just say it's sine. You'll be marked right for either one. And then it will be omega, which is 120 pi, and then this will be minus 166.30 degrees. And that's part 2. Any questions about this part? No? All right, great. Hold on 1 second. Okay. Now, for the last part of the question, what we can find is that we need to find the average power dissipated by the resistor. Now this is actually kind of leading into the next sort of topic, so I might cover the theory for that and I'll come back to this question for the last part. So the last part is about AC power, or the last bit of theory. And so AC power, we've sort of extended the definition from DC power. Naturally, the easiest sort of definition we can get is that we can say that power is just times the voltage at an instant times I at an instant. But the issue with that is that power now is variable by time, and so power can change very quickly, and so it's not really useful. It doesn't really give a meaningful sort of like way of analyzing the power sort of system. So what we do is that we look through the median value. And so the median value is just the average power, which we define like this. And so you can just sort of see that if power was given by some sort of sinusoidal signal, it's not really sinusoidal, the average power would just sort of be the average value of the sinusoid. Just a bit of extra theory if you're interested. And so we use this definition in order to understand power, or to calculate power in the next example and the question, the last part of the question before. And so now we need to find the maximum average power transfer. So this is sort of another AC continuation of the, it's a continuation of the definition from DC. So now we'll say that the load to maximize maximum average power transfer isn't just R Thevenin, it's now the conjugate of, well, it's not R Thevenin anymore, it's Z Thevenin, because we're working with impedances. And this is the new formula for P max, or the maximum average power. And so if we have a restriction as well, so let's just say that the load has to be real, so it's not complex, what we say is that the Thevenin, this will have maximum average power transfer when we take, or when it's equal to the modulus of ZTH, which is a real number. And so if we want to find the power maximum of this, what we could say is that, sorry, that's not what I wanted. What we would say is that we would have to use the generic definition of power. So that would be in terms of the current phases and the voltage phases, which is sort of derived from this. Okay. And then the last part is sort of working with RMS values. So RMS values, the reason why we have them is just because they make working with power more convenient. And for the reason for that is that when we're working with sinusoidal signals, the RMS sort of amplitude for a signal is just going to be the same as the normal sinusoid amplitude divided by root 2. And the reason why this makes things so good is that if we just look at this, for example, if we sort of like pack in the half into each of these amplitudes, we put 1 root 2 into the VM, we put 1 root 2, or 1 on root 2 into the IM, we can actually describe average power as, this isn't actually fully correct, it's this. We can get P equals V, VRMS times IRMS times the cosine of the angle between the phases. And this is convenient because we get rid of the half. That's really it. There's not much more to it, at least not in quad 1. You'll also see that you might have heard of something called complex power or imaginary power or reactive power. It's a concept that used to be in quad 1, but they've moved it over to 2, 1, 3, 4. So all the concepts that you learn for average power in quad 1 are sort of a subset of a larger theory. So just know that when you're working with AC power now, it's not, if there's some things that don't fully make sense, it's just because you haven't learned the stuff yet. You'll learn it if you continue with ELEC quad 1 or ELEC in 2, 1, 3, 4, or if you just look through the textbook, it's probably there as well. All right, so we'll just actually go back to that. We finished this question. So the last part was find the average power dissipated by the resistor. So we want to find the average power through, is it R1? Yeah, it's R1. We want to find the average power through this. And so what we can say is that we know this voltage here. This is 240 milli, angle 0. We know that this is 0 volts. This is 0 volts because it's connected to ground. And so what we can say is that, I'll just write it here actually. We'll know that power is equal to, it will be half times the real part of the voltage phasor times the conjugate of the current phasor. Now, I don't want to work with currents because I don't have it right here, or I can derive it easily, but I don't want to. So what I can say is that I here is equal to V conjugate on Z conjugate. Does that sort of make sense? The way I've done that is I've just applied V equals IR, but I've manipulated the equation, or V equals IZ. And then because we're conjugating I, it's like an operation, mathematical operation, so you have to conjugate the numerator and denominator. Are there any questions so far about this? No? So then what we'll get is that P is equal to half RE, and then we'll get V times V conjugate on Z conjugate. Now the great thing about this is that this, we get, when we're multiplying a number by a complex number by its conjugate, we get rid of the sort of angle, so it becomes very purely real. So what we'll get here is that we'll get V squared, the absolute value of V squared. So this will actually be 240 milli squared. And so what we'll get is that this is half times the real part of V squared on Z. Oh, that's kind of messy. Conjugate. Right. And then we are going a bit over time, aren't we? Yeah. So maybe for the last problem, I'll just sort of tell you guys how I would do it, because we don't have time to do the whole problem. I might do some parts of the question, but I'll just tell you my thought process on how I would solve it. So for this problem, we'll just finish this up real quick. We know that V is equal to, or the absolute value of V is just the amplitude. So this is going to be V1, which is 240 milli. And we know Z conjugate, but we know Z is this, right? And we found that here. This is just Z1 conjugate. So this is actually going to be this, but we make this negative positive. So we get 12289.7 angle, and that'll be positive 12.5. You guys kind of see how I did the conjugate? I just flipped the angle. And so I'll just plug this into my calculator and I'll get this. There is a caveat to this, and I'll explain that in just one moment. Just let me get the actual solution for you guys. So this would be 240 times 10 to the negative 3, and then we'll have to square it, just because, 12289.7, and then the angle would be 12.5. Okay. So if I simplify this, this actually gives me 2.29 microwatts. It's actually pretty small. Small by a factor of times 10 to the negative 6. Now, well, if you're pretty astute, you might have realized that when I was calculating this, I was getting the power. Let me get rid of some of this clutter. What you might have noticed is that when I was finding that power, P, I got it for this, all of this, right? Because this is the whole impedance, right? Now, can anyone tell me why the power for this is actually the same as the power just for the resistor? Does anyone know? Have you done this in your lectures? No? Okay. Well, the reason why is because the power for any reactive element is always 0, the average power. So if you have an inductor, and it's like whatever, the power through that inductor, the average power is always 0. If you have a capacitor, and the average power through this of the capacitor is always 0. So if the power of all of this is whatever we found it, that means if we look at it component-wise, the power, this contributes 0 power, so all of it has to come from the resistor, if that sort of makes sense. And that'll actually make things pretty quick if in the exam you're asked a question like, oh, find the power for all of these elements. From the start, you can say, oh, I can see an inductor here, a capacitor here, and another inductor here. Because of that, I know that all of them have an average power of 0. I can just say that. And so that was actually that's the end of that problem. All right, I'll just quickly go through the last problem. It's actually pretty involved. Yeah, it's quite long. But I can do the first part, and then I'll explain the last 3 parts pretty quickly. So the first part, it asks us to, so we'll look through the circuit. It says determine the RMS value of the source. So that's the source. Oh, this is the source. We know Vm, which is the amplitude, is equal to 100. That means Vrms is just going to be Vm on root 2, which is 100 on root 2. So find the RMS value of the source. So therefore, this just becomes 100 on root 2 angle 45 degrees. That's it. Fairly easy mark right there. We just divide it by root 2. That's the easiest part of this problem. Now, for the next part, it says find RL such that maximum average power transfer is absorbed from the circuit, then find the maximum average power from that RL. So what we're saying is that we've got this. We can tell that this problem is a Thevenin sort of maximum average power transfer problem. So we need to find what resistance here will give us maximum average power transfer, assuming that this has to be real. So what we know from the theory is that if that has to be real, if RL has to be real, then we have to find the absolute value of ZTH. And then from that, we also need to know the VTH in order for us to simplify the circuit and so forth. Now, in order to do this, we want to find the Thevenin circuit, because then what we can do is that if we have to open circuit this, because we're not considering that, we're just considering the rest of the circuit right here. We can turn this into ZTH. That's overlaying on that, and that's not nice. That'd be ZTH. This would be VTH. So we can sort of simplify this circuit to look like that. Now, there's so many different ways you can do this. Honestly, you can build off of one another. So the second part means that you need to find part 2. So whatever RL was, you put it into there. So this becomes some RL. I haven't calculated it, obviously, but you know that RL. And so you'd have this node right here. And so you'd have to go through the circuit, and I would recommend you apply nodal. Nodal will probably be pretty nice here. Or you could simplify this entirety of the circuit right here into one impedance. Then you can do V on Z is equal to I. You get the current through there, and then you do a bunch of current divisions down all of these branches as you go down. And so the reason for that is that we'll find the powers going through all the resistors. Now, back to what I said earlier, we know that the power for this and this are 0. We know the average power of all the reactive elements are always 0. But for the resistors, that's not the case. So what we do is that we'd have to find the current through there using that method I just mentioned. So you would say that this would be the current I, and then you do half times I squared R, and then you'd find the power for this, and then you'd bring this over here, and then if you wanted to, you could do current division. So you could simplify these in parallel. So these are in parallel, then in series. simplify them, then you do current division through this branch, and then you could do current division through this branch, and then you can find the current through the 50. You don't really need to find the current through this, or you don't have to find the current through this, because we already know what the power was. We derived it in the previous section. Find the maximum power transfer in part 2. So that's how you do the third part. And then for the fourth part, it's if the load can be complex. So if we're not working with RL anymore, we're working with ZL. So we're removing that restriction. What we can say is that we want to find the maximum average power transfer dissipated through the load. We know from our definitions, if I go back here, we know that if there's no restriction for ZL, then ZL will just become the conjugate of ZTH. So from part 2, we already found what ZTH is because we simplified the whole circuit. So it would look like this, something like that, ZTH. And then I'll call this ZL. So we know ZL will just be the conjugate of whatever complex number that is. And then in order to find the P max, so the maximum power for this, we would use this formula. So yeah, so what you do is that you take the absolute value of VTH, which we found of the phasor. So it would be this is VTH. This is from part 2. And then you'd square it, and then you divide it by 8 times RTH. So RTH would just be the real part of this. So you can deconstruct this impedance into a real part plus an imaginary part, and you just take the real part. And so you divide it. And so that gives you Pmax. That's all this problem really has going for it. It's quite lengthy, but hopefully through my thought process, you can kind of see how you would solve it. If you just follow it, if you sort of follow it in a systematic approach, then it should be fairly straightforward. All right. Are there any questions at all about this problem or any of the other problems or any of the theory? No? All right. Well, I guess we'll just wrap it up here. We've gone a bit 30 minutes over time. That should be all right. Thank you all for coming. Yeah, if you guys came in a bit late, did say at the start of the crash course, if you could scan this QR code, this helps ELSOC get funding from ARC. You'll be supporting us so that we can make more academic resources, just like this. Other than that, have a great day, guys, I guess. Thank you all for coming. Yeah, all right, clap. All right. And there's no questions in the comment section. Awesome. Yeah, I'll just end the stream real quick, if that's okay.
Just about the superposition thing.
Yeah.
Because one of the, I think.
So which question was this one?
It was